Greetings and welcome, Internet friends. Mr. Waddy here. Today we're taking a look at Algebra 1's textbook, Chapter 9, Section 2, talking about solving quadratics by graphing. And so I'm teaching an Algebra 2 class. We're cross-pollinating our books for the best of both worlds, which is why I'm using multiple resources like that. And so you already know, if you're one of my students, how to solve a quadratic equation. But we only were able to solve certain quadratic equations, specifically ones that were factorable. And our old strategy was I would set the equation equal to 0, I would factor, then using zero product property, set both factors equal to 0 and solve. However, there's a problem. Not all problems are factorable. And so we're going to begin looking at how to solve ones that don't fit in that family. But before we learn how to solve by graphing, all right, using a graph, I'm going to flash back into the world of lines. And so here we go. This is the general idea that we're going to use. The same thing, we'll use the same idea with quadratics in a moment. If I have an equation, say y equals mx plus b. In fact, actually, what is this equation? This is y equals x plus 2, in which the slope is 1 and the y-intercept is 2, right? You remember that. So here's the y-intercept, and then the slope's going up 1 over 1, all that. Now, if I'm solving the equation x plus 2 equals 0, now, yes, I realize you guys all know that you could subtract 2 from both sides and get x equals -2. What I also could do is I could take this, once it's set equal to 0, and make that equal to y. Make the 0 equal to y, or y equals this part of it. All right? And if I then graph this equation, which we've got right here, there's a particular value that I'm going to look for. And that value is the x-intercept. And so notice the x-intercept is -2, -2, and -2 was also the solution we found when solving algebraically. And so this is the idea. If I take an equation and write it as a function, a y equals function, and then graph that equation, then notice the x-intercepts will be the solutions of the original equation. Now, one of the reasons why it's the x-intercept is, notice this. Here, this equation was equal to 0. I changed the 0 with the y, and in the graph, the x-intercepts all happen to have y coordinates that are 0. And so y is 0, y is 0, it's kind of bouncing back and forth between those two things. And so the reason why the only point I'm interested in is the x-intercept, or plural, multiple x-intercepts, is because that's when y was 0. And so it's kind of like this interesting little trick. We'll put it to work. So here we go. A quadratic equation is a non-linear equation that can be written in standard form. Blah. We've done that. In Chapter 7, you solve them by factoring. We've done that. In Chapter 8, we learned how to graph them, and now those powers are going to be combined. So how to solve? Write the equation in standard form. Notice, right, set it equal to 0. Technically, if you write it in kind of vertex form as well, that also would work, or intercepts form. Setting it equal to 0 is the important part. Then graph the related function. So instead of having it equal to 0, notice I figure it out with the y. Then I find the x-intercepts, and if there are any, so sometimes there will be no solution, then the solutions or roots of the equation are the x-intercepts of the graph. Let's just jump right in. So here I've got x squared plus 2x equals 3. I'm going to subtract 3 from both sides. Now, in order to graph, let's figure out my a, b, and c. So a is equal to 1. Then I've got b is equal to 2, and c is equal to -3. Now, there's... Oh, actually... This is still true. Once I got it set equal to 0, I'm technically rewriting it the related equation, y equals x squared plus 2x minus 3. There we go. There we go. And now I'm taking the same a, b, and c. Now, things that we knew from this, we knew that the y-intercept is always the c value for these. And so I know that it's going to plot through the point -3. We had a way of finding from this form how to find the vertex, and h was equal to -b over 2a. And you guys are getting faster at these things, so the full explanation, you can go back to my chapter 8 videos. -2 over 2 is -1, so that's h. To find k, I then took that h and plugged it in for all of the x's. Y'all recognize this. And so I'm going to have x squared plus 2x minus 3, except what I'm doing is replacing the x's with -1s. And you guys can, you've already been assessed on this, so you can speed do these things if you want. 1 minus 2 is -1, minus 3 is -4. So k is -4. So -1, -4. There's my vertex. Now notice, the thing I'm looking for is, once again, the x-intercepts, which I have not yet found. But I've got, all right, where's my colors here? One more trick up my sleeves. I can find the slopes. Tell you what, I'll do a full explanation on this one, and then in the future we'll do the rapido ones. So the classic slopes of a parabola are up 1 over 1, up 3 over 1, up 5 over 1, starting at the vertex, which I've plotted here. Because a was equal to 1, then multiplying all of those by a, it was still the same thing. So from the vertex, I go up 1 over 1, there's my point, up 3 over 1, there's my point, up 5 over 1, there's my point. We also were able to mirror these over the axis of symmetry, which passes through the vertex. And so this was 1 unit away. Here's 1. Here's 2 units away, so 2 over here. Here's 3 units away, so 3 units over here. And then I could draw my graph. Let's see. So purple, 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 purple. Man. Oh, wow. Wow, that was the saddest parabola. Now, I'm not... All right, it's not even that better. Boom. It's good enough, good enough. Now, what am I actually interested in here? Well, I'm interested in the x-intercepts. So I graph these, and notice I have 2 x-intercepts. X-ints were -3 and 1. Now, these are 2 separate points. I could write those as -3, 0 and 1, 0. But I don't think we need to. The only thing you cannot do, don't write that as -3, comma 1 in an ordered pair. But if you want to write -3 and 1 like that, that's fine. You just can't throw it in parentheses, because then it'll look like it was a point. And -3, 1 is not even on the graph. So there you go. So those are my x-intercepts. And the whole point of graphing this was to go back to solving this, which is the same as solving that, which is to say that these x-intercepts are the solutions. X equals -3 and x equals 1 are the solutions of the original equation. Let me just do a quick mental check. -3 all squared is 9, plus 2 times -3. 2 times -3 is -6. 9 minus 6 is 3. It works out. And the same for 1. 1 squared is 1, plus 2 times 1 is 2. 1 plus 2 is 3. Boom. Both of those work out. So it did work. Now, I'll be honest. Graphing isn't my favorite way of solving these. There's going to be a better way in the future. And in this case, this could have been factorable. I agree. But you've got to learn how to do it when it's easy, so you can relate it to those other things. So let's see. What's the... Let's look at one of these. I don't know. So I've got x squared plus x minus 12 equals 0. So then the related equation function would be y equals x squared plus x minus 12. Let's see. Oh, there's the 12 there. So the c value being -12, I know it's off the screen, sorry, is my y-intercept. Let's figure out the vertex real quick. So h would have been -1 over 2 times 1, negative b over 2a. Here's the b, here's the a. So h was equal to -1/2. Oh man, this one's nasty. K, guys, I chose the worst one here. Worst example. -1/2 squared plus -1/2 minus 12. K is going to equal -1/2 squared is +1/4 minus -1/2, same as -2/4, minus 12 is the same as minus 48/4. And you could have reached for a calculator a long time ago. So I got common denominators. 1 minus 2 is -1. Minus that, I've got -49/4. And I am going to reach for a calculator here. 49 divided by 4 is 12.25. And so K is the following. Man. Yeah, this is the worst possible graph, guys. I've got more examples coming. I should probably just do those. But here we go. -1/2, -12.25 right here. It's going to then go up 1, so that's -11.25 over 1, so that's at 1/2. Then up 3, so 1, 2, 3. So now it's at -8.25 and over 1, so it's at 1/2. And then up 5, and so then I'd plot it from there. All right, guys, I'm skipping out. I'm quitting out on this example so fast. You'd end up graphing it, and you'd figure out wherever your x-intercepts are would be the solutions of the original equation. I believe they actually would have ended up landing at -4 and 3, if I'm looking at this right. Yeah. Yeah. That is where they would have ended up landing. So once again, not the greatest strategy. This one ended up being nastier than I thought, and the little scale that I made for you didn't quite give you enough space to plot the points with honor. So here we go. Let's keep going. Let's keep going. All right. Here's another one. So let's set this equal to 0. X squared minus 8x plus 16 equals 0. Also notice this is saying, oh, wait a minute, there's going to only be one real solution in this case. The related function is y equals that. Let's figure out A, B, and C. I'm going to write them over here just for space. A is 1, B is the -8, and Charlie is the 16. Now 16 is way up here, so I don't have space for my y-intercept to show up. But I can find the vertex, -b. So the opposite of -8 over 2 times a. 2 times 1, 8 over 2 is 4. So there's h. And then to find k, plug 4 in there and there. 4 squared minus 8 times 4. This is giving us a lot of practice graphing again. I guess that's a good thing. 8 times 4 is 32 plus 16. Oh, no, it didn't. That's all equal to 0. And so my vertex is at 4, 0. My a value was 1. And so my slopes were 1 over 1, 3 over 1, 5 over 1. And this one's positive, so it opens up. So yeah, so you would have plotted some points, boop, 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 right, mirrored them, and it's a thing of beauty. But the takeaway here is this. My solution is the x-intercept, which the x-intercept, there's only one, not two, and it happened to be the vertex. And so x equals 4, or my x-int was just 4, and the solutions to the problem are just plain old x equals 4. So whatever the x-coordinate of the x-intercept is the solution of this equation, is the solution of that equation. And so in this case, because the parabola ricocheted off that x-axis and hit only one time, this problem only has one real solution. What do you know? What do you know? All right. Here's another trick. Now let's see. Which way did I set this up. I wonder what I would have done here. I'm trying to remember. Hopefully I do it in the same way I did earlier so it lands on my graph right. Method 1 is what we've been doing. Let's say I'm going to add x squared to both sides, so I'd have had x squared plus 2x plus 4 equals 0. Is that going to land in the right spot? I think so. Now wait a minute, that's not factorable. Oh, you know why? Because there's no real solutions. Aha, aha. This is going to be, ooh, wow. So there is no x-intercept. Here we go. Let's find h and k. So h is -2 over 2 times 1. H is -1. K is going to be that -1 plugged in for both of the x's. So -1 all squared plus 2 times -1 plus 4. K is equal to 1 minus 2 plus 4. 1 minus 2 is -1 plus 4 is 3. And so there's my h and k. So -1, 3. Okay, good. I did this right. And it's a regularly shaped parabola, so it's just up 1 over 1, up 3 over 1, and it doesn't even fit on my graph. Now, the point is when I graph this, notice what are the x-intercepts? There are no x-intercepts. Therefore, no solution. There are no real solutions to this problem. Now, we will eventually figure out how to represent those as imaginary or complex solutions, which for my students, we've already done our complex unit, and I'll teach you how to find those later on in this chapter. But graphically, you can see it never crossed the x-axis, and so there were no x-intercepts, and therefore there was no real solution for the equation. All right, so method 1 is always setting it equal to 0 and solving. Okay, let me show you method 2. So when I have -x squared equals 2x plus 4, the other approach is to take both of these and both of these halves and write them as their own equation. So here's y equals -x squared. Here's y equals 2x plus 4. And if I graph both of those equations, if those equations cross where they intersect, I would take the x coordinates of their intersections. And so let me graph the first one here. So let's see. Well, I'll tell you what. This one just happens to be through 0. And the slopes are -1, so it would be down 1 over 1, down 3 over 1, down 5 over 1. And so bop, and bop, right? I just actually moved the screen. That's unfortunate. And so, so here we go. We've got upside down parabola like so. Right? Now, I've also got to graph this over here, which in this case, wait a minute, this is a line. This is y equals mx plus b. So m equals 2, b equals 4. So I'll plot the y-intercept at 4. And the slope is 2, so that's up 2 over 1 is a point. And by the way, that's the same as going down 2 backwards 1. Down 2 backwards 1. Down 2 backwards 1. And if I draw this line, wow, guys, I'm actually super proud of how that line came out. I'm impressed. You'll notice that these two graphs never cross. All right, if there was a point when they cross, let's say that what if the parabola looked like this? Then I would have taken whatever intersection it was, and I would have taken just the x coordinate of that intersection as my solution. But in this case, they never crossed, and so there's no intersection, and therefore there's no solution again. And so both of these approaches verify the same thing. So it turns out with method 2, is what your book's going to call this, you can take each half of the equation and just write it as its own function and then graph them. And sometimes that might be easier. And so that's a perfectly fine approach. Let's see. Here's some method 1 approaches. So here, if I graph this, notice it never crosses, so no solution is what would have happened here. Here, I believe what I did was I did x squared plus 7x plus 6 equals 0. And when I graphed the y equals of this, notice I get 2 values. So my x answers are -6 and -1. And over here, when I graphed, this one's positive, so I must have added x squared to both sides, right? So I would have had x squared plus 2x plus 5 equals 0, and then I would have graphed y equals x squared plus 2x plus 5. And notice, wait a minute, this never crossed, and so this one had no solution. And if I was to use method 2, I would have written 2 separate equations. I would have had y equals 2x plus 5 and y equals x squared, -x squared. Tell you what, let me do, no, that one's not a great example for method 2. I want to do a method 2 where we actually have some solutions, though. Oh, that's crazy up high. That won't even fit if I try method 2. Guys. No, none of my method 2 graphs would work. I wanted to do a method 2 where they actually intersected. Dear. And this one would have ended up intersecting at weird points. The vertex would have been in a weird spot. All right. Well, I'm gonna keep cruising. So here's the general idea. A quadratic equation has 2 real solutions if it has 2 x-intercepts when you graph the related function. It has 1 real solution if the related function has 1 x-intercept, right? 2, 2, 1, 1, none, none, right? And that's how it works. That's how it works. So you can just graph the related function and you're good. You're good to go. Now, it turns out, let's think outside the box. Here, this might be the first time you've seen the graph of a 3rd degree equation. That's right. And they gave it to you in some weird format. I believe later on you'll end up see how to graph polynomials that are not parabolas. Okay, but right now, notice our little tricks still work. If I graphed the related function and I was looking for the zeros of this function, all I've got to do is figure out where does it cross the axis, and this one would have actually had 3 solutions: x equals -1, x equals 2, and x equals 3. And so all you would do is graph it and read it off the graph. I'm not going to give you one of these crazy swoopty-swoops without the graph at this time. So don't you fret. Don't you fret. Now, one of the things, even though some of these have been ugly, like with fractions and stuff, one of them was, yeah, this one, garbage. Even though that has happened, all of our answers have been conveniently integers. It is possible, I want to point out, to have graphs that don't cross at like -4 or -3. They cross somewhere in between. All right, and that is possible, right? Real life doesn't always conveniently land on integer coordinates. So there is a way of approximating the zeros of a function using a graph. And so one of the ways we can do that is like looking at the graph, which I gave you here, or looking at a table. And we could technically generate our own input-output table, okay? But I will have decimal solutions anytime this is not factorable. Not factorable. But just because the original problem wasn't factorable doesn't mean that it doesn't have real solutions. This definitely crosses the x-axis. It's just going to cross at some weird inconvenient place. Now, notice this. This solution is somewhere between -4 and -3. And so notice here, I plugged in values that were between -4 and -3. In fact, I plugged in values between -4 and -3.5 because I realized that it was further to the left, so it was past the midpoint on the left side. And so that's why I picked these as inputs. I've already generated the outputs for those given inputs. You would have, either using technology or a calculator, technically, right, if I had the input of -4, I would have had to calculate what is f of -4. And I would have done -4 squared plus 4 times -4 plus 1, right? I would have replaced the x's with -4s, and I would have evaluated this. 16 minus 16 plus 1, and I would have gotten 1, and there's that same output. And if I plug in a decimal, I happen to get decimal outputs, but I would have plugged in -3.9 right here, -3.9, and it would have been a whole lot of work. Now at this point, I'm not going to have you do a whole bunch of plug and chug in a calculator. This is what I am going to have you do, though. I'm going to have you analyze this. Notice these 3 points are negative, and these happen to be positive. All right, think about it this way. This side of the graph was positive. This side of those values were negative. And somewhere between positive and negative numbers, if the graph is all one connected curve, somewhere it had to equal 0, somewhere in the middle. And so I suspect that the location where it changes direction, it had to cross the x-axis. It did not teleport, okay? And so when I'm looking at a table, the moment I see it go from positive to negative, I know that somewhere in between there was 0. Same thing this way. If it goes from negative to positive, I know that somewhere in between it had a 0. And so what is my estimate for this? Well, notice it says approximate to the nearest tenth. So these are both at the nearest tenth. Which one is a better estimate? Well, I'm going to take this one. I'm going to say x is approximately -3.7. And I'm choosing that one because this was closer to 0 than this, right? Whichever one is closer. Okay, similarly for over here. These ones were negative, right? All of these points were negative. And then suddenly it became positive, right? These points were positive. And so wherever the sign change occurred, somewhere in between, it must have perfectly equaled 0. And so what was the x coordinate when it was 0? Well, let's take a look. Now this one is closer to 0 than that, so I'm going to choose -0.3. And so I get 2 approximate answers for this problem. Feel free to check out at this point. I'm going to just go through one last one. This is the monitoring progress question. Even faster. So it went from negative to positive. Why did I choose these numbers? Because I saw that on the graph, it crossed somewhere between these two numbers, So I chose values between -1 and 0. Okay? I found the ones where it happened to change sign, and this is closer to 0 than this. So I said x is approximately -0.7. For this one, they happen to change sign right here and here. Which one's closer to 0? This one. So I'm going to choose 2.7. And I've got my approximations. And you're welcome that I didn't require you to plug a whole bunch of numbers into a calculator. You're welcome. All right, thanks for watching, Internet friends. Have a good day.